Welcome to qnawire.
Hi, so for this question, we're going to first look at, in general, what is going to happen when we reach the equivalence point for a weak acid. So, at the equivalence point for any weak acid that we're dealing with, we're going to generate A minus plus water. At the equivalence point, we have added the same amount of concentration of each of them. So that equilibrium, I'm going to omit the change because here we're going to assume that this goes to zero, this goes to zero, even though that is not completely true. But we're generating an amount of C0 of A minus. So then we can use this quantity in order to find the pH as A minus reactions with water are going to generate HA plus OH minus. And if we look at the ice table for this, what we're going to get is C0. We're going to get that a certain amount minus X is going to dissociate in water. So it's going to react with the water. So plus X. And at equilibrium, we're going to get C0 minus X, and X. If you look at the weak acids that you're dealing with, all of them are monoprotic weak acids. So I can follow this structure for the equations. This means that this reaction, first of all, corresponds to Kb. This is not the Ka of the acid. Okay? And this is equal concentration of HA, concentration of OH minus, divided by concentration of A minus. So, replacing the values at equilibrium for the concentration, this is x squared divided by C0 minus x. So, if we want to solve for x, this is going to be equal to Kb times C0 minus x square root, right? We can solve for x directly here by solving the quadratic expression that comes from this. But in general and in most cases, since the value for Kb it is going to be a small value, that means that the value for x is going to be in general much smaller than the value for C0. So the approximation that we can make is that x is going to be much smaller than C0. And this simplifies our equation because if that is true, C0 minus x is equal to C0. So our equation over here becomes much simpler, right? And remember that this would be the concentration of OH minus. So after we have solved for this value for all of the acids, what we can get is get the POH and then get pH as 14 minus POH. So in all of the cases that we're going to deal with, we are starting with, we're going to be starting with a zero point 0.1 molar solution that then it is going to react with 0.08 molar of NaOH. But now we are going to have a difficulty because we're not given the volume of my initial solution, we're just given the concentration. So in what other way can I calculate the pH for this solution? Well, the other method that we can use if we're not given those quantities is we are still going to solve for x, but what we can use is Henderson-Hasselbalch equation because this x is also going to be equal to the concentration of HA. So the other way to do it is finding the pH at the equivalence point as pKa plus logarithm concentration of A minus divided by concentration of HA. So this is going to become pKa plus logarithm of x divided by C0. So those are the two methods that we are going to have. Unfortunately, for both of them, in order to calculate the concentration that we are going to have at the equivalence point, we require the volume of the initial solution. In any other way, there's no way for us to know. So what I'm going to do is, in order to perform both of these methods, I'm going to assume that I'm going to have 1 liter of solution. So this liter of solution, since we're going to have a 1-to-1 correspondence in between the weak acid and the strong base that we're going to employ, the amount of moles that we're going to get is going to be 1 liter of solution times my concentration of my weak acid. It is going to be equal to the volume that I'm going to add of the strong acid of OH minus times the concentration of my strong base, right? So the volume of OH minus that would be required, and is going to be 0.1 divided by 0.08, so 1.25 liters. So under this assumption, the volume at equivalence point, it is going to be equal to 2.25 liters. And the amount of A minus at the equivalence point, it is going to be equal to the amount of the weak acid that we have at the beginning, which is nothing but 0.1 mole. Of course, here in theory, they should have given you the volume of the solutions that you're working with, because otherwise there's no way for us to know these values. And you're going to see that both of these methods are actually equivalent. So with this information, the value for C0 at the equivalence point of A minus, it is going to be 0.1 mole divided by 2.25 liters, giving us a concentration of 0.044 periodic molar concentration. Okay, so with this we can proceed and do the calculations. We know that our x is going to be the square root of kb times C0. We know the value for C0, and the only thing that we are left is finding kb for the different acids. So remember that kb is going to be equal to kw divided by ka. Kw is 10 to the minus 14. So we're going to do this for the 3 different acids that we're going to get. For HBr, the value for Ka is equal to 1 times 10 to the 9. This means that this is strong acid. So at equivalence point, the pH is going to be equal to 7, because the reaction is a strong acid with a strong base. So the pH at the equivalence, it doesn't matter the situation, we're going to get a pH of 7. For case B, now we're going to employ this equation. For chlorous acid, HClO2, the Ka is equal to 1.2 times 10 to the minus 2. That means that Kb is going to be equal to 8.33 times 10 to the minus 13. Thus, the value for x, that is the concentration of OH minus, it's going to be 1.92 times 10 to the minus 7, 1945 times 10 to the minus 7. This corresponds to a pOH of 6.7, and the pH, which is 14 minus pOH, is going to be 7.28. Sorry, 6.72, so 7.28, just to keep the quantities with the correct rounding up. And finally, for C, for benzoic acid, the Ka is going to be equal to 6.3 times 10 to the minus 5. That means that the value for Kb is going to be equal to 1.58 times 10 to the minus 10. That means that our value for x, remember this was Kb times C0, which is the concentration of OH minus, as we did before. It is going to be, remember C0 is 0.044444. This is going to be 2.66 times 10 to the minus 6. So POH is equal to 5.575, actually 576. Whoop. Thus, the pH is going to be 8.424. Nice. So with this, the main feature is that for the weak acids at the equivalence point, the pH is going to be larger than 7. And for the strong acid, the pH at the equivalence point, it is going to be directly equal to 7 because we don't have any associated weak base present in our solution. So that would be all for this problem. The only thing that is missing from your question is actually the initial volume of your solutions, but you can ask your professor about that. Remember here that I assumed that we have 1 liter of solution at the very beginning of the 0.1 molar solutions for each of them. Okay? And that would be all. Thank you very much.